Good evening and good morning to the folks, and welcome to the second webinar in our series of autonomous driving related uh, webinars. Today we are thrilled to invite Dr. Marco Pavone of Stanford University to talk about his work on using AI to deal with unpredictable humans on the road. First, let me just say a few words to introduce myself. I'm Vice President of Product at Apex AI. Apex AI is a company based in California, and we develop automotive-grade software for autonomous systems, including cars and robots. We're also founding members of the AutoWare Foundation and contribute significantly to ROS and the AutoWare projects. Please take a look at the Apex AI website and sign up for the course, Self-Driving Cars with ROS and AutoWare, which you'll find over there. It's free, it's open source, and has a wealth of practical information for developers. A couple of housekeeping rules that I want to mention before we get started. We have 1 hour for this talk, and we'll try to keep it on time and wrap up in an hour. Please use the Q&A button that you will see in this webinar to type in your questions. We will take breaks during the presentation so Dr. Pavone can answer those questions. And before I hand off, I just wanted to say a few words about Dr. Pavone. He is the director of the Autonomous Systems Lab at Stanford University and co-director of the Center for Automotive Research at Stanford. His main research interests are in development and methodologies for the analysis, design and control of autonomous systems with an emphasis on self-driving cars and autonomous aerospace vehicles and future mobility systems. He has a PhD in aeronautics and astronautics from MIT, and he received a number of awards, including the Presidential Early Career Award for Scientists and Engineers from President Barack Obama, an Office of Naval Research Young Investigator Award, the National Science Foundation Early Career Award, a NASA Early Career Faculty Award, and Early Career Spotlight Award from the Robotics and Space Systems Foundation. Okay, that was a mouthful. So welcome, Dr. Pavone. Before we get started, I will take this opportunity to send the audience a couple of polls. Please take a look at your screen. You'll see this a poll that we want to just survey the attendees on a couple of demographic questions. First, on your role, whether you are in engineering or other, and if so, what type of work you actually do. I'll let this poll run for a few more seconds and close it, partly for us to get an idea of who we actually have in the audience. Thank you. I'll close the poll now with a lot of folks attending, and I'll actually also share the results with you. Most of the folks today watching this are actually software developers with a good deal of also hardware developers in there. Another question here that I want to ask is about your interest or your experience with interaction between autonomous vehicles and human-driven vehicles. Take a look at your poll to see if this to give us a sense of how relevant this particular topic is going to be for you. Thank you for responding. I'm going to close the poll now with an overwhelming interest in actually considering interaction between autonomous and human-driven vehicles. Thank you so much for that. I will try to keep this quick. I only have a couple more questions here. And this question is to judge the audience interest in deep learning techniques and which part of the autonomy stack you actually use it for, if any. This is a multiple choice question, so select all that apply if you're using autonomy for deep learning techniques for perception, planning, control, fleet coordination, or in fact other. I'm going to end the poll in a few seconds. So the results are that most of the folks using deep learning techniques are actually using it more or less for perception, as 82% of the responses. Planning control are also common, as also actually fleet and other. So it's interesting to note. And finally, one last question. This is just a question to see how plugged in you are to academic research that's often that Dr. Pavone and others publish. All right, ending the poll there. So good to know that we are actually frequent readers of publications on this topic, research publications. So excellent, thank you very much. And with that, I'm going to close the polling, hand it over to Dr. Marco Pavone. Go right ahead.
All right, thank you very much for the introduction, and thank you very much for joining the meetup today. And also thanks to Apex for organizing it. As mentioned, at Stanford, I direct the Autonomous Systems Lab. The goal of my lab is to develop methodologies for the control of autonomous systems. In other words, we work on methodologies to make robots capable of making decisions on their own. A key application domain is represented by space robotics. Before joining Stanford as a faculty, I was a research technologist at NASA JPL in the robotics section, where I was working on the entry, descent, and landing of rovers on Mars. I've also been working on the design of rovers for exploration of low gravity bodies, such as asteroids and comets, where the traditional mobility systems based on wheels do not work well anymore. In particular, the complex topography of low gravity bodies such as a comet, as depicted on the left in this slide, make mobility particularly challenging. Together with JPL, we worked on designing an internally actuated hopping robot that we tested on a microgravity testbed that we developed in my lab. Currently, I'm also working with, in a collaboration with Professor Mark Kutkowski at Stanford, on designing algorithms to grasp and manipulate objects in space. Here I'm showing a video of our robots being tested in zero gravity by leveraging air bearings over a very flat granite table. Specifically, we've been working on a gripper that is loosely inspired by how the gecko feet work. Specifically, the grippers that are depicted on the right-hand side in the slide, future pets that, thanks to directionally aligned microfeatures, become adhesives when loaded in shear stress. We have sent one of these grippers to the International Space Station last year, and we plan to test the gripper together with the autonomy algorithms later this year on the space station. Now, in general, controlling space robots is challenging due to the very complex environments, which gives rise to a number of difficult stochastic effects. But one redeeming feature of space robotics is that in space, you do not have to deal with intelligent forms of life, that is a human. While here on Earth, autonomous systems, and in particular self-driving cars, need to operate alongside the humans, which make the problem quite challenging. And indeed, reasoning about interaction-aware decision-making tool is a key focus of my research and will be the focus of this talk. Specifically, for the rest of the talk, let's focus on autonomous driving. So here in this video, you can see a typical scenario whereby there are vehicles that are trying to merge on a highway. Even though here, the overall intent and overall goal of the people on the road is clear to everyone, there are some cars that are trying to merge. The results of the maneuvers could be quite uncertain, and results and depends on complex and oftentimes fairly aggressive negotiation. Indeed, in general, interaction on the road are really an exercise in negotiation. And autonomous vehicles, and self-driving cars in particular, should be able to perform such a negotiation in order to achieve safe and efficient driving. In other words, autonomous vehicles should be able to perform what I refer to as proactive decision making. That is, they should be able to proactively interact with other agents in order to infer their intents, while concurrently exploiting this information to take actions that account for agent responses. Now, my approach to enable proactive decision making is model-based, whereby a probabilistic understanding of the interaction dynamics I use as a basis for policy construction. This is different from model-free approaches, whereby possible human actions and relative likelihoods are only implicitly encoded in a policy that is learned directly from data. And the rationale behind this decoupling between intent modeling and policy construction is that in this way we can achieve a level of transparency in design that is typically unavailable to model-free approaches. Now, the first step in model-based approaches to interaction-aware decision-making is to devise a model of human intent that allows us to forecast future actions and future trajectories of a human. My work in this area is motivated by 5 key considerations. The first one is that from the perspective of decision-making, we want to be able to predict future actions of a human on the road contingent on what a robot might do in the future in order to capture the interactive aspect of interaction. Second, we are targeting timescales on the order of 1 second. This is with action-reaction dynamics on the order of 1 second. This is different from traditional decision-making that reasons in terms of high-level macro actions at the level of multi-seconds. For example, should I go right, should I go left? And this is different from low-level control aimed at collision avoidance that should recompute actions at the level of milliseconds. So basically, we're in a gray area between high-level decision-making and low-level control. Third, at this time scale, the intent of a human is typically highly multimodal. For example, in this example in the right, I'm considering a traffic weaving scenario whereby a robotic vehicle depicted in white is trying to exchange lane with a human-driven vehicle. Now, a typical use of an intent modeling module is to say, well, if the robot were to accelerate, what could be the possible responses of a human? And at the very least, it's conceivable to imagine that a human is going to showcase 2 modes. One mode whereby the human would decelerate, and another mode whereby the human showcases an aggressive behavior and would accelerate. That's what I mean by multimodality. Or likewise, if the robot were to decelerate, then the human-driven vehicle might have, again, 2 modes, maybe one around accelerating and another one about decelerating. Fourth, we want to be able to predict future actions from a human conditional on the history of the interaction. For example, the past 2-3 seconds of relative position, relative velocities, and so on, in order to uncover latent behavior of a human, such as alertness or aggressiveness. And finally, we would like to have a design that is as interpretable as possible in order to ease debugging and to gain trust in this technology. Now, at a high level, there are 2 main paradigms in order to build model of human intent. The first paradigm, which arguably is the more traditional one, is robotics, is referred to as in this talk as ontological. And the idea is to postulate some structure on how humans make their own decisions. For example, in terms of a cost function that a human is trying to optimize. This is the typical setup, for example, for inverse reinforcement learning. The problem, though, is that the structural assumptions oftentimes are difficult to reconcile with how humans actually operate. Humans are neither adversarial nor cooperative, and this fuzziness of behaviors is difficult to reconcile with ontological or theory of mind methods, as they're called, that is ultimately rooted in game theory. So in the past 2-3 years in my lab, we've been looking at a quite different approach, whereby the idea is that I refer to as phenomenological, whereby the idea is to directly learn from data the probabilistic structure of an interaction. That is, we want to learn action distribution without reasoning about the underlying motivation. And I will be more clear, and I will be clearer about what I mean in a second. Specifically, there has been a lot of work in the past few years from the AI community on how to predict the future, basically, particularly by leveraging so-called generative models. Where our work differs from the norms is that we want to make predictions not only based on past observations, but we also want to reason contingent on what a robot could do in the future. Specifically, we want to learn a probability distribution P that tells us what the action of the human will be at the next time step. So we're assuming that the current time is T, so T plus 1 means future. Subscript of H means human, subscript R means robot. So we want to learn a probability distribution in terms of what the next human action is, conditional on the history of the interaction. X here denotes relative states, such as relative positions or relative velocities. U denotes the stacked controls by the human and the other agents on the road. And critically, also conditional on the future candidate robot action. Conditioning on the history allows us to uncover latent behaviors such as aggressiveness or alertness. And conditioning on future robot actions that are basically motion candidates or motion primitives allow us to capture the interactive aspect of an interaction. In practice, we use a recurrent conditional evaluation autoencoder in order to learn such a distribution. And the way that this model looks like in practice is as follows. Let's assume that we want to model how to predict longitudinal acceleration for a vehicle that is moving alongside an autonomous vehicle. So here on the x-axis, I'm showing time, and on the y-axis, I'm displaying longitudinal acceleration. The current time is about here 0.7 seconds. Solid lines means quantities that have happened in the past. So here in particular, we have the blue line depicts the longitudinal acceleration for the robots. The red line depicts the longitudinal acceleration for the human-driven vehicle. Here you see that for the past 0.7 seconds, the longitudinal acceleration for the robot and the human have been constant, which means that both vehicles have been going at constant speed. So the way we use the generative model is as follows. Let's consider a possible future robot actions whereby we keep going for a while at constant speed, then we accelerate, we coast at constant speed, and then we decelerate. What are the possible behaviors displayed by a human in reaction to this motion profile? And that's how we sample the generative model. For example, here you will see that roughly we have two main modes. One that corresponds for this very simple setting to an acceleration with few samples, which means that with low probability, we will have a human responding in acceleration. And then a bunch of samples that show deceleration, of course, with different possible profiles, portraying the different types of behaviors that a human might display within each high-level latent behavior, so in this case, deceleration. So here I'm showing the case whereby we're trying to predict the future actions for another agent on the road. Actually, we have been extending this base model in a number of directions, particularly in terms of making predictions for several different agents in the scene belonging to different semantic classes, such as humans, bikers, human-driven vehicles, and so on. One of the key features of this model is that we can condition our predictions on a vast class of heterogeneous data. From dynamical information, so basically taking into account that a vehicle has dynamics that are differentially constrained, so very much different from dynamics of a human, all the way to map information from map encoder that allow us to reason about the geometry of the scene. So for example, if you look at some of the trajectory forecasting work out there, you might have that sometimes the predicted trajectories would predict that the vehicle goes off-road. And that is because those forecasting works do not account for road geometry or crosswalks and so on and so forth. The end result is a model that we have recently developed that we call Trajectron++. All code models and data is available on our lab GitHub if you want to give it a try, which is basically a state-of-the-art generative model that explicitly incorporates dynamics and heterogeneous data. In the paper that I'm mentioning here, we go at great length in terms of comparing our models against other models available on the state-of-the-art using GANs or other techniques. And we show that basically we outperform other models quite significantly sometimes. And particularly, we validated our models on a number of data sets. For example, the new scenes data set posted by autonomy up here. But here, I just want to showcase the importance of conditioning in making predictions. So specifically here, I'm showing a scene taken from the new scene dataset, whereby we are at an intersection, and we have a number of agents. We have some vehicles, we have some pedestrians. And in the left panel, I'm showing predictions based on our base model. So we do not reason about the underlying dynamics. So basically, we model as if pedestrians were to have the same dynamics of a vehicle. And we do not reason about the geometry of the scene as captured by, for example, a map. And here you can see that, for example, in the case of this vehicle, the predicted trajectory will undershoot the ground truth that is depicted with the white line. Now, in the center panel, we now account for dynamics. Specifically, we model, for example, vehicles as dynamically extended Dumas vehicle, and the output of the CVAE are actually control actions that are integrated through the differential equations of motion into position. And here you see that now the predictions display two modes. One whereby the predicted behavior is to go more or less straight, and the other one is to turn right. And in particular, the mode where the vehicle would turn right would coincide more or less with the ground truth. Then finally, in the right panel, I also account for the map M through a map encoder. And now you can see that we have one mode only in this case, which now coincides quite well with the ground truth. Actually, the Aptiv had a challenge at the past ICRA conference on predictions based on the new scene datasets. And our model, actually with very minimal engineering and training, was one of the top 3 teams out of about 100 teams that participated. And interestingly, the top 3 teams all used phenomenological models for their predictions, which is quite interesting because until a few years ago, ontological models were really the go-to methods for this type of application. So now here, the takeaway message of this first part of the talk is that phenomenological models, and in particular deep generative models, achieve state-of-the-art performance. And I will pause here to see if there are any questions before proceeding to the second part of the talk, whereby we will discuss how to use phenomenological models for intent prediction for the purposes of decision making.
So I see one question here that I'm going to read out. If there's other questions, please type them out into the Q&A section. The question I have is, does the model take into account the physical limitations of a car? For instance, are there situations where the car knows what to do, but the car cannot physically keep up?
Yes, absolutely, yes. And that's the whole point that I was trying to portray in this slide, where in our most recent work, we explicitly reason in terms of with dynamical models of the vehicles, and more in general, there are other agents on the road, for example, of a bike, and we account for the physical limits for those vehicles. And it turns out, through ablation studies, that actually, in some cases, that dramatically increases the performance of the interprediction trajectory forecasting model. So very good question. And in retrospect, it's a bit surprising that a lot of work out there does not account for dynamics. But one should also consider that much of this research is really has been done it's really been done by the computer vision community. So, for example, a lot of results in these areas are published at the CVPR, SCTV, and so on, where the idea is really less on driving a downstream decision-making pipeline. So there is a little bit less of a concern of explicit reasoning about dynamical systems, which becomes paramount if, of course, you want to start talking about sharp predictions, set assurances, and so on.
See one more question here about how many time steps ahead are the predictions, and how does the computation time scale with the prediction horizon?
Yeah, so we typically predict up to about 3, 4, 5 seconds in the future with this line of work. And in terms of computation and scalability, I'll get back to that in the second part of the talk. Roughly speaking, with a scene with several agents, say 10, 15, and so on, we can have inference times in the order of 3, 4 hertz.
And one final question that I see here, how do you represent the map at the input? Is it a lane graph or a similar structured representation?
Or we just use a mapping encoder. So we just take an ancient map and then we use a mapping encoder.
Okay. Perfect.
And by the way, and all these details are actually discussed in this paper that is posted on my website. And I will show a link to my website toward the end of this talk.
I'm going to ask one more question.
Sure.
Actually, I think if you don't mind, Dr. Pavone, can you just repeat the answer about the map? I think the audio was not very clear.
Oh yeah, we just use a neural net mapping encoder that maps an HD map into different into the road geometry.
Okay. The folks, would you please answer your type in your questions into the Q&A box? It's the one I'm keeping an eye on. But there's one landed in the chat message that I'm going to read out, which is, does all the training already assume the motion info is given? If the motion information is not continuous, would it be different?
I'm not sure I understand the question. So what do you mean by discontinuous? Actually, we should ask back what is meant by discontinuous motion.
Well, if we can clarify that question, we will try again. Otherwise, I'll move on to a couple more here. One is about the size of the data set. What's the size of the data set needed to train or to model and predict a pedestrian's motion?
Yeah, so for the case of traffic wheeling, that's the case where we started with. Basically, we built in my lab an interactive driving simulator where I had 2 humans driving side by side in a number of traffic wheeling scenarios. And we gathered about 2,000 trajectories. That's what we used for training. For the new scene dataset, basically, we fully use the new scene dataset. But the important point here to highlight is that, of course, phenomenological models are much less sample efficient than ontological models. Of course, we put less structure, so they require more data in order to train. But the rationale is that with the wealth of data that is now becoming available, these models actually will be able to be trained and finally eventually outperform ontological methods.
Okay, very cool. So let's park some of the other questions for now and move on to the next part about a interaction-aware decision-making framework.
Great. So Okay, so far I've been talking about trajectory forecasting, but the question is, how do you use such forecasts from the perspective of decision making? So what we do is basically build a library of motion primitives. In actuality, we look at about 4,000 action sequences, for example, that you put here on the right. Some of them can go straight, some other ones are going to the other lane and so on. And for each motion primitives, we generate a sample of possible responses from a sample set of possible responses from a human. In actuality, we look at, we consider about 100,000 responses per computation cycle. And we can do that at about 3-4 hertz. So then what we do is to score the best motion primitive according to some aggregate cost function depicted here as a sum of the JIs, where each JI encodes an objective such as penalty for collision avoidance and incentive to fulfill a task as quick as possible, for example, exchanging lane and so on. And critically, we score the motion primitives by looking at average performance. So basically, we take an expectation over the sample set that we get from the generative model of performance for each motion primitive. Now, a natural question here would be, well, now that you have distributional information about the possible responses of a human, how do you account for that by, for example, infusing a notion of a risk measure? So basically accounting more explicitly for events of low probability and detrimental outcome. So basically swapping the expected value operator with a risk measure that accounts for events on the tail of the distribution, such as mean variance optimization and so on. So due to lack of time, I won't go into the details of this topic, but I will refer you to a paper that I had with a former postdoc of mine, who is now at Princeton, where it's basically a position paper where I express my views on how a robot, in my mind, should account for risk for the purposes of decision making. And that basically entails a trade-off between the three main considerations. A, you want to have a risk measure that you can do computation with. Risk measures typically are difficult to do optimization with. Two, you want your risk measure to capture some reasonable notion of risk sensitivity. And three, you would like to have a risk measure that is interpretable, that is, that you can communicate to other stakeholders. Unfortunately, many risk metrics out there are not very easily to communicate. Like, for example, there is a famous one referred to as conditional value at risk, which is quite difficult to explain to other stakeholders. Anyway, I refer you to that paper, or you can just send an email if you are interested in further discussing this topic. Here now I'm going to show how the decision-making architecture works by considering the driving simulator and interactive driving simulator that I mentioned before. Specifically, as I said, by using a simulator, basically bias VTD. In our case, we looked at a number of scenarios, including traffic weaving, whereby the idea is that an autonomous vehicle wants to exchange lane with a human-driven vehicle. So here you see some human-in-the-loop results, whereby the vehicle, the white one, is driven by our algorithms, and the blue one is driven by a human. On the left-hand side, you see the predictions from the CVAE-based intent prediction model in terms of velocity on the left, in terms of acceleration, in terms of acceleration at the bottom for different candidate robot actions. And here you can see that some interesting behaviors emerge, like, for example, the white vehicle was nudging a little bit the other lane in order to infer the intent of the human-driven vehicle, which looks great until, unfortunately, a disaster happens. So here I'm showing a case whereby the human defies the predictions of the intent prediction model and drives into the robotic car. So this is bad, but I would argue that it is unavoidable, meaning that with probabilistic predictions, your predictions are basically guesses. and sometimes you might guess it wrong. So specifically, uh, at this level of decision making, collisions are unavoidable in some cases because, first of all, with probabilistic modeling, you might guess it wrong. Second, at this level of decision making, collisions is typically incorporated as an additional penalty function amidst different other objectives, and this might cause conflicting objectives. And finally, the planning at 3/4 hertz is ultimately too slow in order to ensure safety. So here the key question at stake is really how do we integrate safety assurance within a probabilistic performance-centered planning framework. Specifically, in this plot, I'm notionally portraying efficiencies versus safety. So I would argue that the high-level planners typically rely on probabilistic reasoning in order to promote efficiency at the expense of safety. Well, low-level planner, basically collision avoidance modules, reason adversarially about the other agents in order to promote safety at the expense of efficiency. So, of course, you can be maximally safe if you don't do anything, so you stay home. And ideally, you would like to be here. You would like to be maximally efficient and maximally safe. Of course, that's not possible. So the question is, how do you trade off between these two competing objectives? So part of my work in the past couple of years has been on how do we integrate a low-level control module aimed at promoting safety within a higher-level probabilistic decision-making module in a way that does not unduly affect performance. And to make a long story short, what we do is to harness techniques from backward reachability in order to reason about interactions at the lowest level of the autonomy stack. Specifically, our full decision-making control stack is as follows. We have a high-level interaction planner that produces a desired trajectory based on forecast for the trajectories of other agents on the road based on our CVAE-based intent prediction model. Then we have another module that is a reachability cache, which encodes the notion of relative unsafe states. It is relative states that might lead to a collision despite the best efforts from the robots. And these unsafe sets critically can be computed offline. And here, this set would be, for example, represented by this geometric figure. And the idea is that if the other vehicle, so the other vehicle on the road, were to enter this region, then there might be situations whereby, despite the best effort from the robots, a collision will be unavoidable. And then the controller uses the actual controller fuses the information from the interaction planner and the reachability cache by computing actions that minimally deviate from the desired planner trajectory whenever the other vehicle enters the avoid set. So basically enters the regions of relative unsafe set that might lead to a collision. In reality, this MPC tracking controller, which uses a fairly detailed model of vehicle dynamics, boils down to solving a QP, a quadratic program, which can be done extremely fast. Particularly, we optimize decision at about 150 hertz. So the interaction planner outputs a desired trajectory at about 3/4 hertz by using all the generative modeling that I explained before. And then we have an MPC controller that considers constraints imposed by a reachability cache, which reoptimize actions at the level of acceleration and steering commands at about 100 hertz. Here I'm showing some tests. And one of the reasons why I'm showing these tests is to say that actually we tested this algorithm on one of the full-scale self-driving vehicles that I have at cars. That's for Automotive Research at Stanford. So these algorithms run for real hardware. And in order to capture interaction dynamics, we deploy the algorithms on the self-driving vehicles. So here, everything is done autonomously. So the perception, the intent, the trajectory forecasting, decision-making, the low-level control, and so on. And then the role of the other agent is played by an RC car, which is remotely controlled. So here the idea is that we want to abuse of our algorithms, so really try to operate in a regime whereby the human behaves in a way that is erratic, so operates in a way that tries to defy the predictions of the intent prediction module. So this is the case where still we are again performing a traffic cleaving maneuver. So here you can see that the RC car actually performed a weird maneuver where it's quite nicely covered from this erratic maneuver, but just minimally going off-road and then continuing, instead of exhibiting overcautious behavior such as stopping. Going back to our previous plot, so here I'm showing some experimental data. So we have a formal definition of safety and efficiency that if you like, we can discuss offline. But basically, the red dots correspond to the execution of our algorithms without accounting for probabilistic predictions. So typically, we are very safe. The higher, the better. But oftentimes, we would stop completely if another vehicle were to enact some erratic behavior. The other end of the stream is when we drive only with the high-level decision-making module on without reasoning about the reachability cache. Here we have typically high-efficient behavior, meaning we complete the maneuver quickly, but sometimes we have collision. While with the NPC tracking controller approach that uses, in a principal way, high-level decision-making and low-level control, we somehow have the best of both worlds. So the key takeaway message here is that safety efficient interaction with decision-making really requires principal blending between probabilistic and adversarial planning. Sometimes this aspect is overlooked, so we tried to put some more principled techniques rooted in reachability theory in order to blend these two facets of decision-making planning. Okay, so again, I will stop it here to see if there are any questions.
Again, reminder, type your questions in Q&A, please. Let me read out one of them. I think you mentioned your conclusion about the 3 hertz being too slow for the planning loop. The question is, what led you to that conclusion?
Oh, because considering a typical speeds and interaction dynamics, it turns out that if you optimize at about 4 hertz, you don't have enough reactiveness in order to react to high-speed maneuvers. So it's basically based on the actual physics of the vehicles and the typical relative speeds of agent-to-agent interactions.
Okay. Another question is about how much of the history of the observed vehicle you're actually taking into account. Question asks, does the prediction use immediate past of the other agents to predict future behavior? If so, is it possible instead to generate a summary of an agent's personality computed recursively throughout the full observed history of the agent?
Yeah, that's a great question. So as I mentioned in the first part of the talk, actually we do condition on the history of the interaction and on possibly even additional attributes. So practically in the example that I showed, we were conditioning over the previous 3-4 seconds of an interaction. Of course, you can extend the history, but that will make the model a little bit slower and a little bit more difficult to train. We found that 3-4 seconds is, at least for the type of maneuvers we looked at, a good compromise. But it's very important to highlight that this is an important feature of the model I presented. In other approaches, for example, rooted in inverse reinforcement learning and market decision process and so on, typically you only account for the current value of the state. It's true that you can account for history through state augmentation, but that leads to a sharp decrease in the computational performance. It's well known that this problem scales badly with dimensionality, so state augmentation is, in my mind, not the most computationally efficient way of handling history for this type of problems.
There's a question about what metrics do you use to assess safety and efficiency?
Yeah, so Here, I should have gone a little bit more into the details of the mathematical formulation. But for example, for safety, we look at the fraction of time that a vehicle, so that another vehicle will be within the reachable set, basically the set of unsafe states. And for efficiency is a measure of how quickly we perform the task, as well as lateral acceleration that basically loses them up to discomfort in the vehicle. And if you're interested, I mean, I exactly said what those two metrics are, but if you're interested in the mathematical formulas that are available in this paper, that is again available on the website.
There's a question that asks how interpretable and debuggable are the results of probabilistic planning?
Yeah, I mean, interpretability is always a difficult notion to define. Having said that, we have a nice decoupling between trajectory forecasting and decision making. So at least if a maneuver by the vehicle is erratic, it's relatively easy to understand whether that is due to the decision-making optimization procedure, maybe because the aggregate cost function was not really reflective of what we want to do with the vehicle, or basically the relative weighting was not properly tuned, or it was due to the intent prediction model. Also, and this is some work that I'm not mentioning today, but we've been doing in the lab, we're doing some work in terms of gaining some interpretability in the latent space of the conditional variation autoencoder. So it turns out that with some additional techniques, you can gain some interpretability in terms of what those latent variables correspond to in terms of high-level behaviors, such as going straight or going right, left, and so on. So there are multiple handles to gain interpretability. Of course, there is not a mathematical definition of interpretability that allows me to say this is 70% interpretable and 80% interpretable and so on. So I'm just showing you more a qualitative assessment of interpretability.
And finally, let me just ask about a question that asks, in a practical application, do you believe certain corner conditions should be handled using manual rules?
Manual rules?
Manual rules, yeah.
Yeah, so absolutely. So at the lowest level of the control hierarchy, you want to have a decision logic that is highly trusted and as simple as possible. For me, manual rules means basically very simple motion primitives that you can enact as a last-ditch effort. The question, of course, is how do you smoothly transition between different modes in the state machine of your vehicle in order to avoid traffic and so on. But yes, ultimately, and it is something that I also do in the context of aerial mobility, the last ditch effort should be something that entails almost zero computation and is highly trusted and very interpretable. And I would claim that the MPC tracking controller gets close to that. It relies on a QP, so it's a convex optimization problem. We can put strong guarantees on how long it takes to solve that QP. We can place strong guarantees in terms of what is the solution that we get in order to going to get a global optimum. So that already comes very close to have strong safety guarantees. But yes, in actuality, I would augment that with an even additional layer, last ditch effort where you can, safety stops and so on according to some motion primitives.
Very good. I think we can go on to the final section. We have about 10 minutes left.
Cool. Yeah, that's where I start getting speculative, talking about my current work. I'm not in a company, so I can talk about my current work without any fear of intellectual property violations. So here now I'm going to talk about some thoughts, research directions that I'm currently doing. And if you have any feedback or suggestions, critiques, I will be very happy to hear those. So the first one is that typically in trajectory forecasting, uh, my work or other works as well, the typical outputs are individual trajectories, either a single individual trajectory or a distribution of possible individual trajectories for the other agents. This makes a lot of sense because then you can have a very clear metrics in terms of evaluating the performance of a trajectory forecasting model by simply uh, basically looking at the distance between the trajectory that you output and the ground truth. But it's quite difficult to use in downstream decision making. As I mentioned before, the way that we do decision making is to consider motion primitives, generate a bunch of trajectories in response, then score the quality of that motion primitive. That is very brute force approach. So something that we are looking at is how do we actually reason about prediction representations that are cognizant of the downstream control applications. So basically producing a representation for future intent, future human behavior that you can really plug easily into the downstream control pipeline. And in particular, we have been looking at the system theoretic formalism, whereby we represent future human behavior according to a dynamical system, specifically according to a linear time-varying system. To be clearer, let's assume that we are in a scenario where there is the robot, so our autonomous vehicle, a human-driven vehicle, and a pedestrian. The idea is to represent this interaction according to a linear time-varying system, where x is the concatenated states, meaning the position velocities for each agent. U is the action of the robot, and W is some noise. So what we learn are not individual trajectories, but actually the system matrices A, B, and C. And in particular here, so X is the concatenated state, X1 are the states for the robot, X2 are the states for the pedestrian, X3 are the states for the vehicle. So for example, in the case of a pedestrian, we could model it as a single integrator. In the case of a vehicle, we could model it according to dynamically extended Dubin's vehicle and so on. The diagonal is not something that we learn. We know the physics of our vehicle. What we learn are the off-diagonal elements that basically capture the agent-agent interaction. And we also account for, in the model, for the action of a robot in order to reason about how the robot actions might impact the agent's behavior. So here the key point, and this is preliminary work, is how do we find alternative representation for interaction dynamics that are more conducive to control applications. Why do I think that this is more conducive to control applications? Where if you now have a representation of interaction dynamics through the lens of a dynamical system, then you can just embed that easily into, say, stochastic MPC or just a normal model predictive control pipeline. In actuality, actually, we look at an ensemble or mixture of a linear time varying system, each component corresponding to a different high-level behavior as captured by latent variables such as going straight, going right. The other direction is how do we account on perception? So overall, how do we better frame trajectory forecasting within the overall autonomy system? Of course, perception is affected by uncertainty, and understanding the perception to translate into prediction. So how do we more tightly couple prediction, perception, and trajectory forecasting? So for example, here on the left, you can see that the objects that are more far away have a lower classification score. So the question is, how do we account for classification score from the purposes of a trajectory forecasting in order to have a calibrated uncertainty at the end? Or another aspect is that perception is quite noisy. For example, here on the left, you can see that the level for the yellow vehicle switches at quite high frequency between being a car and being a truck. And these high frequency switches are quite annoying from a trajectory forecasting model. So the idea is how do we embed the notion of robustness into trajectory forecasting in order to account for that. And finally, we're also working on trying to embed logical structure into trajectory forecasting. So for example, I talked about how we encode a map through a map encoder, for example. But for example, how do we encode the rules of the road? And now if you think about, the trajectory forecasting work that I've shown you does not account for rules of the road, but of course, encoding the fact that you have a stop sign in the scene and so on might provide a bias in your predictions that ultimately lead to better predictions. So to make a long story short, we have been working on, so we have some results that show how some logic formalism, in particular signal temporal logic, can be represented in the same computational graph paradigm that is used for deep learning, which basically means that we can do a few things that are quite interesting in my opinion. First, basically we can embed logic within the deep learning framework. And the idea is that you can, once you do that, you can use these in a number of different ways. For example, you could jointly train a neural net for performance in terms of loss function and robustness with respect to satisfaction of a signal temporal logic specification, thereby embedding logical structure in otherwise uninterpretable model. Or you could use this technique for post facto validation of your neural net. Or you could consider training with embedded logic agents that you could use for intelligent testing in your simulator. But basically, tuning the logical specification, you could tune the behaviors that you want to have your other agents on the road to display in order to stress test the autonomy stack of your vehicle. So there are a number of applications that are possible that I think are quite exciting. Now, to sum up, next generation trajectory forecasting, in my mind, should account in a more explicit way about downstream control applications and about structures, such as logical structures. And in general, the conclusion of this talk is that generative models are becoming a state-of-the-art tool for trajectory prediction. And I'm going to submit for publication and post on my website in a week or so a tutorial paper on this topic. But it's a little bit difficult to integrate within the autonomy stack. So a few ways that we are looking at in order to address this challenge is to find representations that are more conducive to optimization, for example, through a system-theoretic formalism. We're looking at a tighter integration between perception and trajectory prediction in order to properly propagate uncertainties, and finally to add logical structure to our models. With that, I would like to, all our code is available on our GitHub. I'd like to thank my collaborators, primarily Karen Leon, who is a PhD student in my lab, Boris Ivanovic, who is a PhD student in my lab, Adi Schmerling, a former PhD student in my lab, now he's a researcher at Waymo, and of course my sponsors, and you can find all my papers at my website. And thank you for your attention, and we have a few minutes for some final questions, but in general, if you have any additional questions, feel free to email me.
Thank you very much, Dr. Pavone. We have a couple of minutes. Let me see if I can squeeze in a couple of last questions. There's a couple on the deep learning models. I'm going to combine them and throw them together as, can you touch on the similarities and differences between what you propose and the IXI or AIXI framework? And another one about, basically, I think talking about reinforcement learning. And the second one is about backpropagation reinforcing and whether that is possible to use with your planners.
So macro applications?
Backpropagation.
Oh, backpropagation. Yeah, so for example, well, I mean, first of all the neural net models are trained for backpropagation, but the last direction that I showed here, whereby we basically represent signal temporal logic formulas in the computational graph pattern of deep learning, is exactly because we want to leverage backpropagation in order to train neural nets with logical specification embedded in them. So, yeah, the short answer is yes, absolutely. So for the role of reinforcement learning, of course, reinforcement learning can be used in a variety of ways, model-based, model-free. I already explained I already talked about my view of model-free approaches to interaction-aware decision-making. I think they are valuable, but ultimately, maybe because of my aerospace background and so on, I like architectures that are modular in order to better troubleshoot them, gain interpretability, better understanding safety assurances, and so on. So, I mean, in a way, the jury is still out there, but my inclination is to favor more modular model-based architecture.
Excellent. We are out of time.
And
So
of course, and leverage as much as possible prior information and structure. So we know, for example, that the other vehicles are differentially constrained, so no need to learn that from data. We know how to do well low-level control by using PP and NPC. So in my mind, no need to throw that experience away. And even for certification purposes, at the end of the day, I still find it very hard to have a pure reinforcement learning solution without some sort of modularity and optimization around it that is trustworthy.
very cool. We're out of time, so I'm gonna close it at this point. Thank you so much, Dr. Pavone, for giving us this talk. It was extremely useful and insightful to see what you've been working on. I'm sure it was valuable for all the attendees. I can judge that just from the amount of question and answers. Sorry, we couldn't get to every single question, but hopefully we've been able to capture the bulk of them. Thank you for all the
Feel
attendees.
free to email me if you have additional questions.
Very good. Thank you. Thank you to all the attendees, and thank you, and hope to see you at the next meetup on autonomous driving.
Thank you very much.
Bye.